The rainbow is a lie. Why geometry and physics create your personal spectrum. You've seen a rainbow. Everyone has. A brilliant arc of color stretched across the sky after a rainstorm. Red on the outside, violet on the inside, with every shade in between perfectly ordered. It looks like an object, a thing that exists somewhere out there in the atmosphere, something you could reach if you just got close enough. But here's the truth that most people never learn. The rainbow isn't there. Not in the way a cloud is there, or a mountain, or even the rain itself. A rainbow is not an object. It's not made of anything. It doesn't occupy a location in space. What you're seeing is a geometric relationship between the sun, billions of water droplets, and your eyes. Change any part of that relationship, move even a few steps to the side, and the rainbow you see literally ceases to exist. A different rainbow takes its place. Two people standing next to each other are not looking at the same rainbow. They can't be. The geometry forbids it. This isn't a trick of language. It's not poetic. It's physics. And once you understand why rainbows exist, you'll never look at one the same way again. Because what seems like simple beauty, what seems like just color in the sky, is actually a demonstration of wave mechanics, geometric optics, and the electromagnetic nature of light itself. Let's figure out what's really happening. Light and color foundations. Before we can understand rainbows, we need to understand what light actually is. Light is electromagnetic radiation. It's a wave pattern in electric and magnetic fields, propagating through space at 300,000 kilometers per second. But here's the crucial detail. Light comes in different frequencies. The frequency determines everything about how that light behaves and how we perceive it. High-frequency light has short wavelengths. We perceive this as violet or blue. Lower-frequency light has longer wavelengths. We perceive this as red or orange. The middle frequencies give us green and yellow. What we call white light, like sunlight, is not a single pure frequency. It's a mixture, a combination of many different frequencies traveling together. Your eye can't detect individual frequencies directly. Instead, you have three types of color receptors, each sensitive to different ranges of frequency. Your brain interprets the combination of signals from these receptors as color. But the light itself doesn't have color. Color is a perceptual category. What light has is frequency. And frequency is a measurable physical property. Now, when light travels through empty space, all frequencies move at the same speed. Red light and violet light race along side by side at 300,000 kilometers per second. But when light enters matter, things change. Matter is made of atoms, and atoms contain charged particles, electrons. When an electromagnetic wave passes through matter, it interacts with these charges. The electric field of the light wave pushes and pulls on the electrons. The electrons respond by oscillating, and those oscillations affect how the wave propagates. The result is that light slows down inside matter. But, and this is the critical point, different frequencies slow down by different amounts. Higher frequency light, violet and blue, slows down more than lower frequency light, red and orange. This frequency-dependent slowing is called dispersion. And dispersion is the reason rainbows exist. The geometry of a single drop. Let's zoom in on a single spherical raindrop hanging in the air. Sunlight containing all frequencies mixed together approaches this drop. When the light reaches the surface, something happens. The light beam enters the water. But water has a different refractive index than air. This means light travels slower in water than in air. And when a wave crosses a boundary where its speed changes, the direction of the wave changes. This is refraction. It's a purely geometric consequence of the wave speed changing at an angle. Imagine a row of marchers walking across a field. They're walking in a straight line, side by side, moving at a steady pace. Now they encounter a patch of mud. The mud slows them down. If they hit the mud straight on, they all slow down together, and the line stays straight. But if they hit the mud at an angle, one side of the line enters first. That side slows down while the other side is still moving fast. The line pivots. The direction of march changes. Light does the same thing. When it enters water at an angle, it bends toward the perpendicular. The geometry demands it. But remember, different frequencies slow down by different amounts. Violet light slows more than red light. So violet bends more sharply than red when entering the drop. The white light beam has now split into a spectrum. The different frequencies are traveling in slightly different directions inside the drop. These beams travel through the water. Most of the light passes straight through and exits the other side. But some light hits the back surface of the drop from the inside. At this back surface, some light exits into the air, but some reflects. It bounces off the inner surface and heads back toward the front of the drop. This internal reflection is critical. Without it, rainbows wouldn't exist. The reflected light travels back through the drop and approaches the front surface again. Now it exits back into the air, and when it exits, it refracts again. The beam bends again as it crosses from slow water to fast air. Violet bends more, red bends less. The separation increases. The light that emerges has been bent twice and reflected once. And because of dispersion, each frequency emerges at a slightly different angle. If you could track the path of red light versus violet light through the drop, you'd see that they come out at different angles relative to the incoming sunlight. Red emerges at about 42 degrees from the direction of the incoming light. Violet emerges at roughly 40 degrees. This 2-degree spread is small, but it's everything. From one drop to an arc. Now let's pull back and think about millions of raindrops, suspended in the air during or after a rainstorm. The sun is behind you, low in the sky. Light from the sun travels past you and strikes raindrops ahead of you. Each drop refracts, reflects, and disperses the light, sending different frequencies back at different angles. Here's the key question. Which drops send light toward your eyes? Not all of them. Most drops are oriented such that the light they redirect goes off in some other direction. But certain drops, at certain positions relative to you and the sun, happen to be aligned just right. For red light to reach your eyes, it needs to come from drops that are positioned 42 degrees away from the antisolar point. The antisolar point is the direction exactly opposite the sun. If the sun is behind you, the antisolar point is straight ahead. So red light reaches you from drops that form a circle, 42 degrees away from that antisolar direction. Violet light reaches you from drops 40 degrees away. The other colors fill in between. You see an arc, not because the rainbow is an arc-shaped object, but because your eye collects light from drops arranged in a cone of specific angles. If you could see the entire cone, if the ground weren't blocking your view, you'd see a full circle. Pilots sometimes do see circular rainbows from the air, but from the ground, you only see the upper half, an arc. Now here's where it gets personal. The angle to each drop is measured from your eye. If you move, the anti-solar point moves. The set of drops that are 42 degrees from your position changes. Someone standing a few meters away from you has a different anti-solar point. They're seeing light from a completely different set of drops. It's a different rainbow. This is not metaphorical. It's not that you're seeing the same rainbow from a slightly different perspective. You're literally seeing different light from different drops arranged in a different geometric pattern. The rainbow you see is your rainbow. Nobody else can see it. And when you move toward where the rainbow appeared to be, the geometry shifts. The rainbow moves with you, always maintaining the same angular relationship. You can never reach it because it's not a destination. It's a viewing condition, an alignment of angles that depends on where you are, where the sun is, and where the rain is. This is why rainbows feel magical. They seem to exist in a location, but they retreat as you approach. It's not magic. It's geometry asserting itself. Advanced clues. Sometimes, if conditions are right, you'll see a second, fainter arc above the primary rainbow. This is the secondary rainbow, and it's created by light that reflects twice inside each raindrop before exiting. The path is more complex. Light enters the drop, reflects off the back, travels forward, reflects off the front from the inside, travels back again, and then exits through the back of the drop. Each reflection and refraction follows the same rules. Dispersion still happens, but the extra reflection reverses the order. In the secondary rainbow, red is on the inside and violet is on the outside. The colors are flipped, and the angle is larger, around 51 degrees, which is why the secondary rainbow appears above the primary. The region between the primary and secondary rainbows often looks darker than the rest of the sky. This is called Alexander's Band, named after Alexander of Aphrodisias, who wrote about it nearly 2,000 years ago. The darkness happens because of the way light is distributed by angle. There are simply fewer paths that send light into that specific angular range. It's a shadow cast by geometry. And if you look very carefully at a bright rainbow, you might notice faint bands of color inside the primary arc. These are supernumerary arcs, and they're evidence that light is a wave. When light exits a raindrop, different paths can interfere with each other. Waves from slightly different trajectories can add together or cancel out, depending on whether their peaks and troughs align. This interference creates a pattern of alternating bright and dark bands, each with a faint tint of color. You need precise conditions to see them. The drops must be small and uniform in size. But when they appear, they're confirmation that light behaves as a wave, not just a particle. It's a quiet detail, easy to miss, but it encodes the same physics that produces the double-slit experiment and the wave-particle duality that defines quantum mechanics. Rainbows are not just colorful, they're diagnostic. They reveal the wave nature of light directly, right there in the sky. So what does it mean that a rainbow is not an object? It means the world is more subtle than our intuition suggests. It means that what we perceive is often a relationship, not a thing. A pattern that emerges from the interaction of light, matter, and geometry. Rainbows don't exist independently. They exist because of you, your position, your eyes, the specific angle at which you're viewing scattered light. This doesn't make them less real. It makes them conditional. Real in the sense that the experience is genuine and the physics is objective, but not real in the sense of being an independent object you could touch or photograph from any angle. Every photograph of a rainbow is also observer-dependent. The camera occupies a position. It has a lens. The geometry applies to it too. And this principle extends far beyond rainbows. Sunsets are geometric. The reddening of the sky happens because blue light scatters more than red light. The colors you see depend on the path length through the atmosphere, which depends on the angle of the sun relative to you. Mirages are geometric. Refraction in layers of air at different temperatures creates images that seem displaced from their source. Even shadows are geometric. They're regions where light paths are blocked, creating a pattern of absence. Physics governs these phenomena completely. No exceptions. No mystery. Just waves, particles, fields, and geometry playing out according to rules we understand. The rainbow proves this in a way that's accessible to anyone. You don't need instruments. You don't need equations. You just need rain, sunlight, and the willingness to think carefully about what you're seeing. What looks like an arc of color in the sky is actually a story about electromagnetic waves, material dispersion, and the relationship between observer and phenomenon. It's a reminder that the universe is comprehensible, that beauty and physics are not separate, that the questions you ask about everyday experience can lead you to deep truths about how reality works. So the next time you see a rainbow, try this. Take a few steps to the side. Watch it shift. Recognize that what you're seeing is not the same as what anyone else sees. Notice that it exists because you exist, positioned just so, looking in just the right direction. And ask yourself this: if something as simple as a rainbow is not an object, but a relationship? What else that seems solid and obvious might turn out to be contingent? What other pieces of everyday experience are actually patterns in perception, governed by physics you haven't noticed yet? Think about that. The world is full of answers, waiting for the right questions.